Silence does not mean absence. In the velvet dark between galaxies, where no wind stirs and no voice echoes, something moves, not with roar or rupture, but with the patience of eternity. Gravity. It pulls without hands, binds without chains, guides without command. A ghost in the architecture of the cosmos, bending starlight into arcs, sculpting spiral arms from chaos, cradling planets in orbits older than life itself. And yet, it is the weakest whisper in the symphony of forces. A magnet lifts a paperclip against the entire mass of Earth, while electromagnetism crackles with fury and the nuclear forces wield titanic power in atomic hearts. Gravity lingers, quiet, slow, almost apologetic. It does not shove, it does not strike, it waits, and everything, eventually, falls toward it. But what if falling is not being pulled, but sinking? What if gravity is not a force reaching out, but the echo of time itself, collapsing beneath mass? A wrinkle in the fabric of duration, where moments gather weight and slope downward, drawing matter along with them. An apple does not fall because Earth calls. It falls because time has grown weary beneath it. A star does not orbit a black hole because it is lured. It glides along the memory of collapsed futures, etched into space-time like grooves in ancient vinyl. And if gravity is memory, then the universe is not unfolding. It is remembering every orbit, every collapse, every silent plunge into darkness. Not creation, but recollection. The cosmos, vast and glittering, may be nothing more than the afterimage of a deeper truth, an event already concluded, replaying in slow decay, a whisper from the beginning, still falling, still folding, still echoing through the hollows of what was. It began with a fall, not a cataclysm, not a revelation shouted from mountaintops. Just an apple, red, ripe, indifferent, detaching from its branch in the quiet orchard of Woolstop Manor. It fell, as apples do, without ceremony, but in the mind of the man who watched it, Isaac Newton. That descent unraveled the heavens. For centuries before, gravity had been a local phenomenon, Earth's private embrace, a tether binding all things terrestrial. The moon danced beyond its reach. The planets obeyed celestial mechanics, divine or mathematical, but separate. Newton saw no boundary. He saw symmetry. The same invisible hand that pulled the apple downward also held the moon in orbit, not by magic, not by divine whim, but by a single, elegant law. Every mass attracts every other mass across any distance, with a force proportional to their product. F equals G mg r squared, a formula so simple it could be carved into stone, and so profound it rewrote destiny. Suddenly, the cosmos operated by rule, not revelation. Comets bent to calculation. Tides answered to lunar arithmetic. The universe, once a mystery whispered by priests and poets, now hummed with predictable harmony. Gravity was a force, invisible, yes, but measurable, universal, democratic. It touched everything, from dust motes to stars. Yet even Newton knew the flaw in his triumph. He could describe gravity's behavior, but not its nature. What reached across the void, what carried its whisper. He called it action at a distance, a phrase laced with unease. How could the sun, 93 million miles away, tug the earth without medium, without messenger? Newton offered no mechanism, only mathematics, only silence. Centuries passed. Telescopes grew, calculations refined, but the question remained: what is gravity, truly? Then came Einstein, not with new equations at first, but with a question that unraveled everything. What if falling is not movement, but stillness? In 1907, while working at the patent office in Bern, Albert Einstein experienced what he later called the happiest thought of my life. Imagine a man falling from a roof. As he plummets, objects in his pocket, keys, coins, a pocket watch, float beside him, weightless. To the falling man, gravity vanishes. There is no pull, no force, only free motion. This was not illusion. It was equivalence, Einstein realized. Gravity and acceleration are indistinguishable. A person in a windowless elevator cannot tell if they are standing on Earth or being accelerated through space at 9.8 meters per second squared. The sensation is identical. The physics, identical. This became the equivalence principle, the seed from which a new cosmos would grow. By 1915, after 8 years of mathematical torment, Einstein unveiled general relativity, a theory not of force, but of geometry. Gravity, he proposed, is not a pull between masses. It is the curvature of space-time itself, the four-dimensional fabric woven from the threads of space and time, warped by the presence of mass and energy. Mass tells space-time how to curve. Space-time tells mass how to move. The Earth does not pull the moon. The sun does not drag the planets. Instead, the sun sits like a heavy stone on a stretched rubber sheet, and the planets roll along the contours it creates, not because they are attracted, but because they follow the straightest possible path through bent geometry. These paths are called geodesics, the cosmic equivalent of great circles on a globe. In curved space-time, straight is curved. Motion is geometry. It was a revolution not of instruments, but of perception. The world needed proof. In 1919, British astronomer Arthur Eddington led an expedition to Principe Island off the coast of West Africa. His mission: to witness a total solar eclipse and to measure whether starlight grazing the sun's limb would bend under the weight of its gravity. According to Newton, light massless should ignore gravity entirely. According to Einstein, space-time near the sun is so warped that even light must follow its curve. Starlight passing close to the sun should deflect by precisely 1.75 arcseconds twice. Newton's prediction. On May 29th, as the moon slid across the face of the sun and darkness fell over the Atlantic jungle, Eddington exposed photographic plates. Weeks later, after painstaking measurement and comparison with reference stars, the result was clear. Einstein was right. The newspapers called it a triumph. Revolution in science, declared the Times of London. Newtonian ideas overthrown. The public, still reeling from the mechanized horrors of the Great War, embraced a new kind of hero, not a soldier, but a thinker whose equations bent the universe itself. But beneath the headlines lay something deeper. Einstein had not merely corrected Newton, he had redefined reality. Gravity was no longer a mysterious tug across emptiness. It was the shape of existence, the contour of time and space, molded by matter. The cosmos was not a stage upon which events unfolded. It was the stage, alive, flexible, responsive, and yet something lingered. In Einstein's equations, time was not a backdrop. It was a dimension, interwoven with space, stretchable, compressible, warped. Near massive objects, time slows. Clocks at sea level tick slower than those on a mountain. GPS satellites must correct for this daily, not as theory, but as engineering necessity. This was not metaphor, it was measurement. Atomic clocks on airplanes, synchronized before flight, return desynchronized, not by error, by relativity. Time itself flows differently depending on gravity's grip. The stronger the gravity, the slower the tick, the deeper the well, the longer the second dot. So if gravity bends time, is gravity not, in part, time? Not just the curve of space, but the collapse of duration. Consider an object in freefall feels no force. It is weightless. Why? Because it is following space-time's natural contour, agilisic. But in that motion, time is not uniform. For the falling object, time flows differently than for the observer standing still. The falling clock ticks slower as it descends deeper into the gravitational well. Gravity, then, is not merely the warping of where things are, but of when they are. Mass doesn't just bend space, it thickens time, slows it, collects it. Like sediment settling at the bottom of a river, time accumulates where gravity is strong. And objects fall not because they are pulled, but because they move toward regions where time flows slower, toward the past's density, toward duration's residue. This is not fringe speculation. It emerges directly from the mathematics of general relativity. The gravitational time dilation term in Einstein's field equations is inseparable from the curvature term. You cannot have one without the other. Gravity is space-time curvature, and space-time curvature includes temporal distortion as fundamentally as spatial. So what if falling is not descent through space, but drift into slower time? What if gravity is not a force of attraction, but a gradient of memory? Here, the mystery deepens. Newton saw gravity as a law, universal, mathematical, impersonal. Einstein saw it as geometry, dynamic, responsive, woven into the structure of reality. But what if both were glimpsing fragments of something older? Consider the equations. In general relativity, the curvature of space-time is determined by the stress-energy tensor, a mathematical object encoding mass, energy, pressure, momentum. But time is not merely a coordinate in these equations. It is a participant, a player. Its rate of flow is part of the curvature. Its gradient contributes to the apparent force in regions of strong gravity near neutron stars. Black holes, time dilates dramatically. An observer far away would see a falling object slow, redden, freeze, not because it stops moving, but because its time stretches toward stillness. From the falling object's perspective, it crosses the event horizon in finite time. But to the outside universe, it never does. It lingers, an echo, a memory. This is not poetic license. It is physics. The black hole's event horizon is not a physical barrier. It is a surface of infinite time dilation, a boundary beyond which time, as the external universe knows it, ceases to flow. To fall in is not to be destroyed, but to be removed from the causal future of the outside world. The object's timeline becomes disconnected. It's now no longer intersexed with ours. It becomes memory. And so the question returns, heavier now, if gravity slows time, and time, when slowed infinitely, becomes memory, then is gravity not the mechanism by which the present becomes the past? Is every falling apple not just obeying a law, but surrendering to duration's accumulation? Is every orbit not a path through curved space, but a spiral through thickening time? Einstein himself resisted such interpretations. He clung to determinism, to a block universe where past, present, and future coexist eternally, and time is illusion. But his equations whisper otherwise. They speak of flow, of gradient, of asymmetry. Time does not merely exist, it behaves, it responds, it drags. Modern physics inches closer to this truth. In 2015, the LIGO Observatory detected gravitational waves, ripples in spacetime, from colliding black holes over 1 billion light-years away. The signal, named GW150914, lasted 0.2 seconds, a chirp, a sigh. But encoded within it was the death cry of two singularities merging, and with them, the final collapse of their shared time. The waves were not disturbances in space alone. They were disturbances in spacetime, temporal distortions propagating at light speed, stretching and compressing time itself as they passed through Earth. Atomic clocks, had they been sensitive enough, would have ticked irregularly during the wave's passage, not by much, by less than 1/trillionth of a second, but measurably, detectably real. Gravity, then, is not static geometry. It is dynamic memory, propagating, evolving, carrying with it the imprint of violent pasts. Even the quantum realm hints at this, though general relativity and quantum mechanics remain unreconciled. Recent theoretical work, particularly in the study of entanglement, entropy, and the holographic principle, suggests that spacetime itself may emerge from deeper quantum information structures. In this view, gravity is not fundamental. It is thermodynamic, statistical, a side effect of entropy, of information loss. And what is entropy, if not the arrow of time? The tendency of systems to move from order to disorder, from memory to forgetting. In 2017, physicist Eric Verland proposed emergent gravity, the idea that gravity is not a fundamental force, but an entropic force arising from changes in the information associated with positions of material bodies. In his framework, gravity is a consequence of the universe's tendency to maximize entropy, to forget, to remember less. If true, then gravity is not the sculptor of time, but its echo, its residue, the shadow left behind as quantum information settles into equilibrium. Falling, then, is not motion through space, but diffusion through memory's gradient, toward higher entropy, toward the erased. Back to the apple. Newton saw law, Einstein saw geometry, but perhaps both glimpsed something older, something quieter. The apple falls not because Earth pulls, but because time thickens beneath it, because the presence of mass slows duration, and motion follows the slope of that slowing. The apple seeks not a force, but a memory, the memory of stillness, of equilibrium, of time's deepest pool. And if this is so, then every orbit, every collapse, every silent plunge into a black hole is not an event in time. It is time itself. Remembering the 1919 eclipse did more than confirm a theory. It cracked open the door to a deeper truth, that gravity is not separate from time, that the two are braided, inseparable, co-constitutive. And if gravity is the curvature of time as much as space, then perhaps the universe is not expanding into emptiness, Perhaps it is collapsing into memory. Each galaxy, each star, each falling leaf, not moving forward through time, but sinking into it. The cosmos, vast and glittering, may be nothing more than the afterimage of duration, a slow, silent fall through the residue of moments already lived. Gravity, then, is not the architect of the future. It is the archivist of the past, and every object that falls is not beginning a journey. It is returning home to where time gathers, thickens, and finally stills, to where all things eventually become memory. There is a silence in physics, not of absence, but of resistance. While the universe hums with forces, the electric crackle of lightning, the nuclear fire in stars, the magnetic dance of auroras, one force remains aloof. Gravity does not shout, it does not spark, it does not split atoms or bind quarks. It lingers at the edge of equations, refusing to join the chorus, alone, unquantized, UNMER, GED. It is the universe's quiet architect, shaping galaxies, bending light, holding planets in their courses, yet in the language of modern physics, it speaks a dialect no one else understands. To grasp the depth of this isolation, one must first understand the unity that gravity refuses. In the 20th century, physics achieved a symphony of convergence. Electromagnetism, once thought separate from the weak nuclear force that governs radioactive decay, was unified in the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg. Their electroweak theory revealed that at high energies, electricity and magnetism are facets of a single force, and the weak force merges with them later. Quantum chromodynamics described the strong nuclear force, the glue binding protons and neutrons, as an exchange of gluons between quarks. Together, these three forces, electromagnetic, weak, strong, form the standard model of particle physics, a tapestry woven from quantum fields where forces are carried by particles, photons for electromagnetism, W and Z, bosons for the weak force, gluons for the strong. All obey the rules of quantum mechanics. All submit to probability, uncertainty, and wave function collapse. All except gravity. Gravity stands apart not only in theory, but in strength. Consider a child's magnet, no larger than a coin, can lift a paperclip, overcoming the gravitational pull of the entire Earth. Electromagnetic force between two protons is approximately 10 times stronger than their gravitational attraction, a number so vast it defies intuition, a 1 followed by 36 zeros. If gravity were scaled to the strength of a whisper, electromagnetism would be a supernova's roar. And yet, gravity rules the cosmos. It shapes the large-scale structure of the universe. It governs the fate of stars. It bends the path of light across billions of light-years. Its weakness is its paradox, for it is precisely because gravity does not cancel, does not shield, does not repel, that it accumulates. While electromagnetic charges neutralize positive and negative balancing to zero, mass only adds. Gravity, feeble in the small, becomes sovereign in the large. But why is it so weak? No known symmetry explains it. No particle carries it cleanly in quantum terms. Attempts to describe gravity as a quantum force to find its carrier, the hypothetical graviton, have stumbled against mathematical infinities. When physicists try to calculate gravitational interactions at the quantum level, the equations explode into nonsense probabilities greater than 1, energies that spiral to infinity. Renormalization, the mathematical trick that tames the other forces, fails utterly here. Gravity resists, quantization. It refuses to be small. The conflict is not merely technical, it is foundational. Quantum mechanics describes a universe of probability, where particles flicker in and out of existence, where observation collapses waves into particles, where entanglement links distant objects faster than light. General relativity describes a universe of geometry, smooth, deterministic, where space-time bends like fabric under the weight of mass, where time flows differently depending on location, where black holes warp causality itself. These two pillars of modern physics are individually triumphant. Together, they are incompatible. At the center of a black hole, the singularity density becomes infinite. Space-time curvature, infinite. Quantum effects, unavoidable. Yet no theory exists to describe it. In the first moments of the Big Bang, when the entire universe was smaller than an atom, quantum gravity must have governed. Yet no equations survive the collision of scales. Even in the gentle curve of space-time around Earth, the conflict whispers. Quantum fields fluctuate everywhere, even in vacuum. These fluctuations should generate energy, vacuum energy, which, according to general relativity, should curve space-time dramatically. Calculations suggest the universe should be curled into a microscopic knot or ripped apart by repulsive gravity. Instead, it expands gently. The mismatch between predicted and observed vacuum energy, the cosmological constant problem, is off by 120 orders of magnitude, the worst prediction in the history of science. Gravity does not merely resist unification, it mocks it. And so, quietly, a radical thought began to surface. What if gravity is not a fundamental force at all? What if it is not woven into the quantum fabric, but emerges from it, like temperature emerging from the motion of molecules, like pressure emerging from countless collisions, like the flow of a river emerging from the chaos of individual water molecules? Not at first, but the anomalies piled up in 1995. Physicist Ted Jacobson published a paper in Physical Review Letters, titled Thermodynamics of Spacetime, the Einstein Equation of State. In it, he demonstrated something astonishing. Einstein's field equations, the very heart of general relativity, could be derived from thermodynamic principles, specifically from the relationship between entropy, temperature, and energy at the boundary of local spacetime regions. Gravity, he suggested, might not be geometry imposed on the universe, but geometry that arises from deeper statistical laws. From entropy, the idea was subtle, almost heretical, but it planted a seed. Then came Verlinde, in 2010. The Dutch theoretical physicist published On the Origin of Gravity and the Laws of Newton, a paper that sent tremors through the foundations of physics. Verlinde proposed that gravity is not a fundamental interaction, but an emergent phenomenon, a consequence of entropy and information. His argument unfolded like a thought experiment. Imagine a particle floating in space. Now imagine that space is not empty, but filled with microscopic degrees of freedom. like a vast cosmic hard drive storing quantum information. When the particle moves, it affects the distribution of this information. Entropy, the measure of disorder, of hidden information, changes. And according to the laws of thermodynamics, systems evolve to maximize entropy. Verland showed that this entropic tendency, this statistical drift toward higher entropy, produces a force indistinguishable from gravity. In his framework, gravity is not mediated by particles. It is not a field. It is not even geometry in the primary sense. It is a side effect, an illusion born of ignorance. The universe pulls objects together, not because of attraction, but because configurations with masses closer together have higher entropy. Falling, then, is not motion through curved space, but diffusion toward higher disorder, toward forgetting. The implications were staggering. If gravity emerges from entropy, then space-time itself may be emergent, not fundamental. The smooth, continuous stage of Einstein's relativity may be a strained approximation, like describing a gas by its pressure and temperature. Without tracking every molecule, this aligned eerily with another radical idea, the holographic principle, first proposed by Gerard 't Hooft and later developed by Leonard Susskind. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary, like a hologram, where a 3D image is stored on a 2D surface. Applied to gravity, it implies that space-time and gravity with it may be a projection of quantum information living on a lower dimensional surface. In 2013, physicists Juan Mendocina and Leonard Susskind proposed EEPR, a conjecture linking entangled particles, EPR pairs, with wormholes Einstein-Rosen bridges. Entanglement, a purely quantum phenomenon, might geometrically manifest as space-time connections. Gravity, again, not fundamental, but woven from quantum threads. Experimental whispers began to echo these theories. In 2016, a team led by Margot Brouwer at Leiden Observatory tested Verland's emergent gravity against observations of over 33,000 galaxies. They measured gravitational lensing, the bending of light by mass, and compared it to predictions from both dark matter models and Verland's entropy-based gravity. The results? Emergent gravity matched the data without requiring dark matter. Dark matter, the invisible scaffolding thought to hold galaxies together, has never been directly detected. Its existence is inferred from gravitational anomalies. Stars orbit galactic centers too fast. Galaxy clusters bend light too strongly. Cosmic structure formed too quickly. For decades, physicists searched for WIMPs, exions, sterile neutrinos, particles that might account for this missing mass. But what if there is no missing mass? What if gravity itself behaves differently at galactic scales, not because of unseen matter, but because its entropic nature becomes dominant? Verland's equations predicted galaxy rotation curves with startling accuracy, no dark matter required. The gravitational pull, attributed to invisible halos, might instead be the signature of emergent spacetime, responding to visible matter alone. The physics community reacted with cautious fascination. Some called it a breakthrough, others a coincidence. But the door had cracked open. The weakness of gravity, once a mystery, now found a possible explanation. If gravity emerges from the statistical behavior of underlying quantum information, its feebleness makes sense. It is not a force battling others on equal footing. It is a shadow, a residual effect, a thermodynamic echo, like the faint pressure of air. Molecules against your skin, imperceptible, unless magnified gravity is the gentle drift of information. Equilibrium, its scale is cosmic not because it is strong, but because it is cumulative. Because entropy, unlike charge, does not cancel. Because information, once displaced, seeks to spread, and in spreading, pulls. Even black holes whisper support. In 1974, Stephen Hawking discovered that black holes are not truly black. They radiate slowly, faintly, due to quantum effects near the event horizon. Hawking radiation implies that black holes have temperature. And if they have temperature, they must have entropy, vast entropy, proportional to their surface area, not their volume. This was the first concrete link between gravity, thermodynamics, and information. Jacob Bekenstein had proposed it earlier, that black hole entropy is S equals A4, where A is the area of the event horizon in Planck units. A radical notion that the maximum entropy in any region is not determined by its volume, as intuition suggests, but by its surface. Again, the holographic principle. Again, the suggestion that space-time is not the foundation, but the facade. So gravity's solitude begins to look less like failure and more like revelation. It does not unify with other forces because it is not of the same kind. Electromagnetism, the nuclear forces, these are interactions within space-time. Gravity may be the shape of space-time itself, and space-time may be emergent. From this perspective, the incompatibility between quantum mechanics and general relativity is not a flaw to be fixed, but a clue to be followed. Quantum mechanics describes the microscopic constituents. General relativity describes their collective behavior, like fluid dynamics emerging from molecular chaos, like temperature emerging from kinetic energy. Gravity, then, is not broken. It is secondary. This reframes everything. The falling apple, not pulled by force, but drifting toward higher entropy. The orbiting planet, not tracing a geodesic in fundamental spacetime, but following the statistical gradient of an emergent geometry. The bending of starlight, not the warping of a primary stage, but the refraction of information's flow. Even time, that elusive dimension woven into gravity's equations, may be emergent. In quantum gravity approaches, like loop quantum gravity or causal set theory, time does not exist at the fundamental level. It arises from relations between events, from the accumulation of quantum correlations. If time emerges, and gravity is the curvature of time, then gravity, too, is memory. Not memory as metaphor, but as mechanism. The universe does not remember in the human sense, but entropy increases. Information spreads. Configurations evolve toward equilibrium, and in that evolution, patterns recur. Structures stabilize. Histories sediment into geometry. Gravity is the slope of that sedimentation. Some physicists resist. The mathematics of emergent gravity remains incomplete. Verlin's theory, while predictive in galaxies, struggles with cosmological scales and gravitational waves. Quantum entanglements link to space-time geometry, while mathematically elegant in toy models, lacks experimental verification. The graviton, though elusive, remains the favored path for many, but the silence of gravity, its refusal to quantize, its thermodynamic echoes, its holographic hints grows louder. Perhaps the deepest shock is not that gravity is weak, or that it resists unification, but that it may not be real, at least not in the way the other forces are real. It may be like the wind, not a thing, but a pattern. Like the wave, not an object, but a behavior. Like the echo, not a voice, but a memory of one dot in this light. Einstein's geometric vision was not wrong, but incomplete. Space-time curves, mass shapes it. But beneath that curvature lies something older, something quieter. Information, entropy, time's slow forgetting. And so the cosmos unfolds, or perhaps refolds, not governed by gravity as a force, but shaped by it as a consequence of quantum uncertainty, of entanglement, of information seeking, equilibrium, of time accumulating, thickening, slowing, until motion becomes memory, and memory becomes geometry. Gravity, then, is not the first law of the universe, it is the last sigh of its deeper truths, rising like mist from a river at dawn. From the quantum waters beneath, a whisper, a residue, an echo of something already gone and still falling. Time does not flow, it falls, not like water, swift and visible, but like dust in still air, drifting imperceptibly toward gravity's gathering weight. Near a mountain, time slips slower than in the sky above. Near a star, slower still. Near a black hole, it slows to a crawl, then stops. Not metaphorically, not poetically, measurably, mathematically, relentlessly. This is not philosophy. This is instrumentation. Atomic clocks, precise to within a billionth of a second per day, have confirmed it. Place one on the floor, another on a shelf. The lower clock ticks slower. Send one into orbit. It races ahead of its earthbound twin. Gravity does not merely bend space, it thickens time. And in that thickening, the universe reveals its deepest secret. Gravity may not be a force acting upon time, but time itself, collapsing under the weight of existence. The first whispers came not from telescopes, but from satellites in the 1970s, as engineers prepared the Global Positioning System, a constellation of orbiting timekeepers meant to guide ships, planes, and missiles. They faced an anomaly. The clocks aboard the satellites, calibrated to perfection on Earth, began to drift, not by error, not by malfunction, by relativity. According to Einstein's general relativity, time flows faster in weaker gravitational fields. GPS satellites orbit 20,000 kilometers above Earth, where gravity is weaker than at the surface. Their clocks, uncorrected, would gain 45 microseconds per day compared to ground clocks. Simultaneously, special relativity dictated that their high 14,000 kilometers per hour would cause their clocks to lose 7 microseconds per day due to velocity-based time dilation, the net effect. Satellite clocks run 38 microseconds faster each day, a trivial number, until one considers that light travels 300 meters in 1 microsecond. Uncorrected GPS locations would drift by over 10 kilometers per day. Navigation would fail. Missiles would miss. Smartphones would point to empty fields. Engineers had no choice. They built Einstein's equations into the system. They slowed the satellite clocks before launch, not mechanically, but mathematically, compensating for both gravitational and velocity effects. And it worked perfectly. Every time a phone maps a route, every time a plane lands in fog, every time a hiker finds their way home, they are guided not by Newton's absolute time, but by Einstein's elastic time. Gravity's invisible hand does not merely pull on matter, it pulls on duration itself. Time is not universal. It is local, personal, shaped by mass, by motion, by memory. But the true depth of this revelation lies not in satellites, but in singularities, black holes, those gravitational abysses where matter collapses beyond recovery, are not merely regions of infinite density. They are regions of frozen time to an outside observer. An object falling toward a black hole appears to slow as it nears the event horizon, the point of no return. Its light reddens, its motion decelerates. At the horizon, it seems to stop, suspended forever in the last moment before disappearance. Not because it halts, but because time, for the distant watcher, stretches infinitely at that boundary. The falling object, from its own perspective, crosses the horizon in finite time. But its timeline, its sequence of nows, becomes causally disconnected from the rest of the universe. It vanishes not into darkness, but into a different temporal fabric, a timeline that no longer intersects with ours. The event horizon is not a wall of matter. It is a surface of infinite time dilation, where the future for the infalling object becomes orthogonal to the future of the external cosmos, where time, as we know it, ceases to flow. Gravity, here, is not curvature alone, it is cessation. This raises a question, quiet, persistent, haunting. Is mass warping time? Or is time's collapse the origin of mass's pull? In Einstein's equations, the answer is symmetric. Massenergy tells spacetime how to curve. Curved spacetime tells massenergy how to move. But symmetry does not imply causality. Which comes first, the mass or the slowing of time? Consider a neutron star, a city-sized remnant of a dead sun, where a single sugar cube of matter weighs 1 billion tons. Time at its surface flows 30% slower than in deep space. An observer far away would see all processes on the star, nuclear reactions, magnetic pulses, even the spin of particles, stretched, slowed, deepened in duration. But what if the slowing of time is not the effect, but the cause? What if mass does not create gravity, but reveals where time has already collapsed? In Verlin's emergent gravity, mass is not the source of gravitational pull. It is the marker of entropy. The presence of mass displaces microscopic quantum information, increasing entropy in its vicinity. Objects move toward it, not because they are attracted, but because that direction holds more microstates, more disorder, more forgotten configurations than this view. Time dilation is not secondary, it is primary. The slowing of time near mass is not a consequence of gravity, it is gravity. The force is the statistical drift toward regions where time has thickened, where entropy has accumulated, where the past has sedimented into geometry. Falling, then, is not motion through space, but descent into slower time, into memory. The mathematics trembles at this threshold. In Scrivi Einstein field equations, G_mu nu equals 8 gt underscore mu nu. The left side describes spacetime curvature. The right side describes mass and energy distribution. But embedded within g underscore mu nu is the metric tensor, the mathematical object encoding both spatial distances and temporal intervals. Time is not a parameter. It is a coordinate, warped, stretched, dilated. Solutions to these equations: Schwarzschild for non-rotating black holes, Kerr for rotating ones, all contain the same signature: time slows near mass. The metric's time component, g, dips toward zero at the event horizon. Time, mathematically, vanishes, and yet quantum mechanics insists that time is not fundamental. In quantum gravity approaches, loop quantum gravity, causal dynamical triangulations, quantum graffiti, spacetime is not smooth. It is granular, discrete, emergent from more basic quantum relationships. Time does not flow, it is counted. In loop quantum gravity, time arises from the evolution of spin networks, abstract graphs encoding quantum geometry. In causal set theory, spacetime is a collection of discrete events ordered by causality. Time is the sequence, not the stage. If time emerges, and gravity is the curvature of time, then gravity too must emerge, not from particles, not from fields, but from the entanglement of quantum bits, from the correlations between events, from the growth of entropy, from the loss of information. Experiments in quantum laboratories now brush against this mystery. In 2020, physicists at the University of Waterloo and the Perimeter Institute conducted tabletop experiments probing the link between gravity and quantum entanglement, using superconducting qubits cooled near absolute zero. They simulated entangled systems and measured how their mutual information influenced effective spacetime geometry in the model. The results were suggestive, not conclusive, but aligned with the ER equals EPR conjecture. Entangled particles behaved as if connected by microscopic wormholes. Geometry emerged from correlation, spacetime from entanglement. In another experiment, researchers at the University of Vienna measured time dilation effects on quantum superpositions. They placed cesium atoms in superposition, existing in two locations at once, and observed how the differing gravitational potentials at each location caused the wave function to decohere. Gravity didn't just bend trajectories, it unraveled quantum states. It enforced classicality. It was active, selective, decisive. Black holes deepen the enigma. Hawking radiation, the slow evaporation of black holes due to quantum fluctuations at the horizon, implies that black holes have temperature. Temperature implies entropy. Entropy implies microstates, hidden configurations beneath the surface. Bekenstein and Hawking calculated that entropy S equals A4, where A is the area of the event horizon in Planck units, not volume, area. Again, the holographic principle, information encoded on the surface, not within, but entropy is the arrow of time, the measure of forgotten states, the accumulation of the past. If a black hole's entropy is proportional to its surface area, and its gravity is proportional to its mass, and its time dilation becomes infinite at the horizon, then gravity, entropy, and time are not merely related. They are facets of the same phenomenon. The black hole does not have gravity. It is a knot of collapsed time, wrapped in entropy, radiating memory. Even cosmology whispers confirmation, the expansion of the universe, accelerating, driven by dark energy, may itself be an entropic effect. In 2016, Gradient of the Cosmic Horizon. The universe expands not because of repulsive gravity, but because information at the horizon drives a thermodynamic pressure outward. Dark energy, then, may not be a substance, but a consequence. Origin, then the fate of the cosmos is written not in mass or energy, but in memory's decay. Scientists now wrestle with equations where geometry, entropy, and information bleed together, indistinguishable. In the gravity equals thermodynamics paradigm. Einstein's equations resemble the laws of fluid dynamics emergent from microscopic chaos. Jacobson's 1995 derivation showed that if one assumes the Clausius relation delta Q equals TDs, holds four local Rindler horizons, accelerated observer boundaries, then Einstein's equations emerge naturally. Gravity is not imposed, it is inferred. In Verlin's 2016 extension, Emergent Gravity and the Dark Universe, he derived modified gravitational laws that reproduce galaxy rotation curves without dark matter. His key insight, at galactic scales, the entropy displacement caused by baryonic matter generates an additional elastic response in emergent spacetime, mimicking dark matter's gravitational pull. The math is complex, and spacetime responds. Time does not flow uniformly. It thickens where entropy gathers, and motion follows the gradient. Gravity is not a force, it is the statistical sigh of quantum information seeking equilibrium. Even the Planck scale, the smallest meaningful unit of spacetime, 10 meters, hints at this. At this scale, quantum fluctuations should make spacetime foam-like, bubbling with virtual black holes, wormholes, topological defects. Time loses meaning. Causality phrase. Geometry dissolves into probability. Yet, from this chaos, smooth spacetime emerges like the surface of the ocean, emerging from the churn of countless molecules, and with it, gravity. Not as a fundamental interaction, but as a collective behavior, a thermodynamic inevitability. The falling apple returns not as symbol, but as signal. Newton saw law, Einstein saw geometry, modern physics sees entropy. The apple falls not because Earth pulls, but because the quantum information beneath it has rearranged, increasing entropy in the direction of the ground. Time flows slower, there not as effect, but as essence. The apple drifts towards slower time because slower time holds more microstates, more forgotten configurations, more equilibrium. It falls into memory. And so the investigation circles back deeper. Is gravity the curvature of spacetime? Yes, but spacetime may be emergent. Is gravity caused by mass? Yes, but mass may be a marker of entropy displacement. Is gravity a force? No, not in the quantum sense. It is a gradient, a tendency, a statistical drift. Is it time's collapse? Increasingly, the evidence suggests yes. Time does not merely slow under gravity. Gravity is the slowing of time, the thickening, the sedimentation, the accumulation of moments into geometry. Mass does not bend time, it reveals where time has already bent itself. The universe is not a machine governed by forces. It is a memory unfolding. Satellites and supercomputers, quantum simulators probe entanglements linked to geometry. Gravitational wave detectors listen for echoes of space-time's quantum grain. Each result tightens the knot. Gravity is not broken. It is not incomplete. It is not incomplete. It is not resisting unification. It is whispering its true nature, not as force, not as field, not as particle, but as time's echo. As entropies slope, as memories wait, and so the cosmos breathes, not in space, but in time, not expanding outward, but collapsing inward, not building the future, but remembering the past. Every orbit, every fall, every silent plunge into darkness, not an event in time, but time itself, folding, thickening, still becoming, still remembering, still falling. The universe is haunted, not by ghosts, but by absences, vast halos of invisible mass cradle galaxies, holding them together against the centrifugal fury of their spinning stars. An unseen energy permeates the void, accelerating the expansion of space itself, tearing galaxies apart with quiet, relentless force. These are not minor anomalies. They are the dominant features of the cosmos, accounting for 95% of its total content. Dark matter, dark energy. Names given not to things understood, but to gravitational behaviors unexplained. And gravity, that quiet, ancient force, sits at the center of both mysteries, not as solution, but as question. What if these phantoms are not substances at all? What if they are echoes, distortions in the fabric of time, misinterpreted as mass? What if dark matter is not matter, but memory? What if dark energy is not energy, but time unraveling? The equations tremble, the cosmos whispers, and the mystery, already profound, deepens. It began with rotation. In the 1930s, Swiss astronomer Fritz Zwicky peered into the Coma cluster, a swarm of galaxies bound by gravity, and found something impossible. The galaxies moved too fast, far too fast. Their visible mass could not hold them together. They should have scattered like startled birds, yet they remained bound by something unseen. Zwicky called it dunkel materie, dark matter. Decades later, in the 1970s, astronomer Vera Rubin confirmed the anomaly, not in clusters, but in spirals. She measured the orbital speeds of stars around the Andromeda galaxy. Newton and Einstein both predicted that stars farther from the galactic center should move slower, like planets in the solar system. But Rubin's data showed no such decline. Stars at the edge raced as fast as those near the core. The galaxy's visible mass was insufficient. Something else, invisible, massive, pervasive, must be holding it together. The scientific response was unified. Dark matter must exist. A new particle, weakly interacting, massive, cold, must flood the cosmos, forming halos around galaxies, sculpting the large-scale structure of the universe. Experiments launched, detectors buried deep underground, particle colliders strained to produce it. Decades passed. No direct detection, no confirmed signal, only silence, and then a heresy. In 2016, Eric Verland proposed that no such particle was needed, that the anomalous rotation curves, the gravitational excess attributed to dark matter, could be explained if gravity itself changes behavior at galactic scales. Not because of unseen mass, but because of emergent space-time responding to entropy gradients. His equations matched observations. Without invoking a single dark particle, the galaxies were not held by ghosts, they were held by geometry. Geometry born of information, of time's thickening, of entropy's pull. Dark matter then might not be matter at all. It might be the shadow of collapsed time. Even more unsettling is dark energy. In 1998, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search, measured the brightness of distant Type Ia supernova. These stellar explosions serve as standard candles, their intrinsic luminosity known, their distance deducible from apparent dimness. By comparing distance with redshift, the stretching of light, due to cosmic expansion, astronomers could reconstruct the expansion history of the universe, expected to find that expansion was slowing, braked by gravity's pull. Instead, they found it accelerating. Space itself was stretching faster with time, as if repelled by an invisible force, a force given a name, dark energy. Later measured by the Planck satellite and other observatories, dark energy now accounts for 68% of the universe's energy density. It is the dominant constituent of reality, and no one knows what it is. The simplest explanation: Einstein's cosmological constant posits that empty space has intrinsic energy. But quantum field theory predicts this vacuum energy should be 10 times larger than observed. The worst mismatch in physics, a failure not of measurement, but of understanding. And so, again, gravity whispers alternatives in Verlin's framework. Dark energy arises naturally as the entropic force of the cosmic horizon, the boundary of the observable universe. Just as a black hole's horizon carries entropy, so too does the cosmological horizon. The universe's expansion is not driven by repulsive gravity, but by the thermodynamic pressure of information accumulating at its edge. Time, here, is not flowing forward, it is stretching outward. Dark energy may not be a substance, it may be time's unraveling. The acceleration of the cosmos is not merely mechanical, it is temporal. As space expands, the cosmological horizon recedes. More volume enters the observable universe, but with it, more entropy, more microstates, more forgotten configurations. The universe, in expanding, increases its information capacity, and with it, its entropic pressure. This pressure pushes not on matter, but on space-time itself. The equations of emergent cosmology suggest that the Hubble parameter, the rate of cosmic expansion, is tied directly to the entropy gradient at the horizon. The faster the horizon grows, the stronger the entropic push. The result: acceleration, no dark energy required, only time expanding, thinning, forgetting. And then the black holes, where gravity reaches its extreme, time reaches its end. At the event horizon, time dilation becomes infinite. To an outside observer, infalling matter freezes, suspended in the last tick of its clock. But quantum mechanics insists that information cannot be destroyed, that every quantum state must be preserved, even across horizons. Stephen Hawking shattered this certainty in 1974. He showed that black holes radiate slowly, faintly due to quantum fluctuations near the horizon. Virtual particle pairs, born from the vacuum, are torn apart. One falls in, the other escapes. The black hole loses mass, it evaporates. Over eons, it vanishes. But if the black hole disappears, what happens to the information it swallowed? This is the black hole information paradox, a wound in the fabric of physics. Quantum mechanics demands information preservation. General relativity, via Hawking radiation, suggests information loss. The two cannot both be true. Solutions emerged, each more radical than the last. In 1997, Juan Maldacena proposed the ADS-CFT correspondence, a mathematical duality, suggesting that a gravitational theory in a volume of space is equivalent to a quantum field theory on its boundary. Information is not lost, it is encoded holographically on the horizon. The black hole's interior is an illusion, a projection of surface data. In 2012, the firewall paradox erupted. Physicists Ahmed Almhiri, Donald Maroff, Joseph Polchinski, and James Sully argued that to preserve information, the event horizon must be a searing wall of high-energy particles, a firewall incinerating anything that crosses. Smooth spacetime, they claimed, is incompatible with unitary quantum evolution. The debate rages still, but beneath it all lies a deeper truth. Gravity is entangled with information, not metaphorically, fundamentally. Hawking radiation carries away entropy, but if information is preserved, that entropy must be compensated elsewhere. The horizon must encode the infalling data. The geometry must remember. Gravity, then, is not merely curvature, it is memory. Consider the implications. If a black hole's entropy is proportional to its surface area, and entropy is the logarithm of microstates, and microstates encode quantum information, then the event horizon is not a boundary in space. It is a boundary in memory. Crossing. It is not annihilation, but archival. The infalling object does not vanish. It is written into the hologram. Its timeline becomes part of the horizon's data. Its motion, its mass, its quantum state, all preserved, scrambled, encoded. Gravity does not destroy, it records. And so the mystery escalates. Dark matter, perhaps not matter, but the entropic response of spacetime to visible mass. Dark energy, perhaps not energy, but the thermodynamic pressure of an expanding horizon. Black holes, not destroyers of information, but its keepers, all tied not to new particles or fields, but to the nature of time itself. If gravity emerges from entropy, and entropy is the arrow of time, then gravity is not shaping the future. It is preserving the past. The equations deepen. In 2020, physicist Thanu Padmanabhan showed that Einstein's equations can be derived from a thermodynamic principle applied to spacetime's local horizons, not just black holes, but any causal boundary. Gravity, he argued, is the thermodynamic limit of an underlying quantum gravitational theory, where spacetime is not smooth, but pixelated, and time is not continuous, but counted. In this view, the cosmological constant dark energy is not a parameter to be tuned. It is the residual entropy of the universe's birth, the memory of the Big Bang, still exerting pressure. The expansion of the universe is not an explosion into emptiness. It is the slow diffusion of primordial information, spreading, thinning, cooling, driving space-time outward as it forgets its origin. Even the arrow of time, that inexorable march from past to future, may be gravity's child. In a perfectly symmetric universe, no gravity, no expansion, time would have no direction. Entropy could increase or decrease with equal probability. But gravity breaks the symmetry. It clumps matter. It forms stars. It collapses black holes. It creates gradients of density, of temperature, of entropy, and with gradients come flow. Time flows because gravity remembers, because collapsed regions, black holes, galaxies, planets hold more entropy than uniform space, because the universe evolves toward higher disorder, and gravity is the map of that evolution. Without gravity, time would be static. With it, time falls. Laboratories now test these ideas at quantum scales. In 2022, researchers at the University of California, Berkeley, placed nanoscale diamonds in superposition, each containing a nitrogen vacancy center whose spin state could be measured. They suspended the diamonds at different heights in Earth's gravitational field, a difference of mere micrometers, and observed how the gravitational time dilation between them caused dicoherence in their quantum states. Gravity did not merely bend trajectories, it selected timelines. The experiment confirmed time dilation is not passive. It is active. It enforces classicality. It erases quantum possibilities, not randomly, but directionally, toward slower time, toward higher entropy, toward memory. Cosmological simulations echo this. In emergent gravity models, when researchers simulate galaxy formation using only visible matter, an entropic response, no dark matter particles, the resulting structures match observations. Spiral arms form. Rotation curves flatten. Gravitational lensing bends light, precisely as seen by Hubble and the James Webb Space Telescope. The invisible scaffolding vanishes in its place. Geometry shaped by time's collapse. And so the question returns heavier. Now if time collapses under mass and gravity, is that collapse? Then is gravity not a force, but a record, not a cause, but an afterimage? Consider a star collapsing into a black hole. From the outside, its surface freezes at the horizon, light reddening, time stretching, motion slowing to stillness. The star does not vanish. It lingers, imprinted on the horizon, encoded in Hawking radiation, preserved in entropy. Its gravity does not disappear, it intensifies. But what is that gravity? Not the pull of hidden mass, but the weight of frozen moments, the curvature of arrested time, the echo of a timeline now severed from ours. The same may be true of the cosmos itself. The accelerating expansion, dark energy, may not be a force pushing outward. It may be time thinning the universe, forgetting its density, its heat, its unity, and in forgetting, stretching each galaxy, receding not because space inflates, but because time between them dilutes. The future is not being built, it is being erased. And dark matter, perhaps not halos of WIMPs, but contours of collapsed duration. Regions where time has thickened under the weight of visible stars, and spacetime, emergent and elastic, responds by curving, mimicking the presence of mass. The galaxy does not need dark matter to hold together. It needs only time, slowed, pooled, accumulated beneath its spiral arms. The mystery deepens, not into darkness, but into clarity. Gravity is not failing to unify, it is revealing its true nature, not as a force among forces, but as time's residue, as entropy's slope, as memory's weight in black holes, in galaxies, in the void between clusters. Gravity does not act, it archives. It does not pull, it preserves. It does not shape the future. It mourns the past, and so the cosmos unfolds, or perhaps refolds. not expanding into emptiness, but collapsing into memory. Each supernova, each collision, each silent fall into darkness, not an end, but an inscription, a line in the ledger of duration, a whisper in the archive of time. Gravity, then, is not the architect of the universe, it is its librarian, cataloging every fall, every orbit, every breath of light, not as events, but as echoes, not as forces, but as memories, still falling, still remembering, still collapsing into the quiet, into the dark, into time's final gentle sigh. Reality is not carved in stone. It is written in equations, some sharp, some blurred, some still half-formed in the minds of those who dare to question the silence between stars. Gravity, that oldest and quietest of cosmic architects, has worn many masks across the centuries. To Newton, it was law, immutable, mathematical, universal. To Einstein, it was geometry, the curvature of a four-dimensional stage where matter and energy danced. To quantum theorists, it is a missing note, a phantom particle, elusive. To modern heretics, it is not force at all, but memory, not cause, but consequence, not fundamental, but emergent. Each theory is a lens, each a mirror. Each reflects not only the cosmos, but the assumptions, the hopes, the limits of the minds that shaped it in its own way. Whispers the same haunting truth. Gravity may not be what it seems. Einstein's vision remains the most elegant. In 1915, he unveiled general relativity, not as correction, but as revelation. Space and time were not passive containers. They were dynamic participants, woven into a single fabric, space-time, molded by the presence of mass and energy. Gravity was not a force reaching across emptiness. It was the shape of existence itself. Planets orbited not because they were pulled, but because they followed the straightest possible path through bent geometry. Light bent not because it was tugged, but because it traced the contours of warped duration. The mathematics was flawless. The predictions confirmed. Mercury's orbit, gravitational lensing, time dilation, gravitational waves, black holes, all emerged not as guesses, but as inevitabilities. Yet even Einstein knew the flaw. His equations broke down at the singularity, where curvature became infinite, density unbounded, time meaningless. They offered no quantum description, no particle, no uncertainty, no wave function. At the smallest scales, where the universe was born, where black holes die, general relativity fell silent. It was classical, deterministic, continuous. The quantum world is none of these. Quantum field theory, triumphant in describing electromagnetism. The strong and weak nuclear forces stumbles at gravity's threshold. In its framework, forces are mediated by particles, photons for light, gluons for the strong force, W and Z bosons for the weak. Gravity, by symmetry, should have its own, the graviton, a massless spin-2 particle exchanged in gravitational interactions, carrying the force like a messenger between masses. The mathematics permits it, the logic demands it, but detection remains impossible, not for lack of trying, but for lack of scale. Gravity is so weak that a single graviton's interaction would be drowned in noise, a trillion times stronger. Even the most sensitive detectors, LIGO, Virgo, future space-based interferometers, measure collective ripples in space-time, not individual quanta. The graviton if it exists, may forever remain theoretical, a ghost in the machine, inferred but never seen. Worse, when physicists attempt to quantize gravity directly to write a quantum field theory of curved spacetime, the equations collapse into infinities. Renormalization, the mathematical trick that saves the other forces, fails. Probabilities exceed 1. Energies explode. The framework fractures. Gravity resists quantization not because it is subtle, but because it may not belong in the quantum zoo at all. It may not be a force to be quinged. And the heresy of emergence. In 2010, he proposed that gravity is not fundamental, not a force, not even geometry in the primary sense. Instead, it is an asterisk, entropic force, asterisk, a statistical tendency arising from the behavior of underlying quantum information. His argument unfolded like a thermodynamic parable. Imagine space not as emptiness, but as a vast reservoir of microscopic degrees of freedom. Quantum bits, entangled, fluctuating, encoding the positions and states of all matter. When a massive object appears, it displaces this information. Entropy, the measure of hidden configurations, changes. And according to the second law of thermodynamics, systems evolve to maximize entropy. This evolution produces a force, indistinguishable from gravity, in Verlaine's framework. An apple does not fall because Earth pulls, but because the configuration where the apple is closer to Earth has higher entropy. Falling is not attraction, it is diffusion, motion toward equilibrium, toward forgetting. The implications cascade, Newton's law. F equals gmjmr squared emerges not from fundamental interaction, but from entropy gradient. Einstein's equations, not from geometric axiom, but from thermodynamic identity. Even dark matter, the invisible scaffolding of galaxies, vanishes. Its gravitational effects are reproduced by the elastic response of emergent spacetime to visible matter alone. Gravity, then, is not written into the universe's code. It is compiled, emergent, approximate, statistical, like temperature, emerging from molecular motion, like pressure, emerging from collisions, like the wave emerging from water. This aligns eerily with another radical vision, the holographic principle. First articulated by Gerard T. Hooft and refined by Leonard Susskind. It proposes that all the information contained within a volume of space can be fully encoded on its boundary, like a hologram, where a 3D image is stored on a 2D surface. Applied to gravity, it suggests that spacetime and gravity with it is not fundamental. It is a projection, a shadow, a lower dimensional quantum system casting a geometric illusion into higher dimensions. In 1997, Juan Maldacena gave this idea mathematical flesh with the ATS-CFT correspondence, a duality, showing that a gravitational theory in anti-de Sitter space, a negatively curved spacetime, is equivalent to a conformal field theory, a quantum theory without gravity on its boundary. Gravity, in this view, is not real in the bulk. It is encoded on the edge, a black hole's interior, an illusion, its entropy, stored on the horizon, its evaporation, a quantum computation on a surface. The universe, then, may not be 3D plus time. It may be 2D plus time, with gravity as the holographic artifact of deeper quantum correlations. And now, the most speculative, Yet most poetic interpretation, the collapse of time hypothesis, not a formal theory, not yet published in peer-reviewed journals, but a synthesis drawn from the edges of relativity, thermodynamics, and quantum information, that gravity is not the curvature of spacetally. It is the fossil of temporal contraction. Wherever mass gathers, time slows, not as effect, but as essence. The presence of mass marks where time has elapsed, where duration has thickened, pooled, sedimented into geometry. Objects fall, not because they are pulled, but because they drift toward regions where time flows slower, toward higher entropy, toward greater equilibrium, toward the residue of moments already lived. Each orbit, each collapse, each silent plunge into a black hole, not an event in time, but time itself. Remembering, in this view, gravity is not a force governing motion, it is the scar of time's passage, the wrinkle left behind as quantum possibilities decohere, as entropy increases, as the universe forgets its initial state. The Big Bang was not an explosion into space. It was the first collapse of time, the moment duration began to thicken, to differentiate, to accumulate, and gravity. The echo of that collapse, still propagating, still folding, still falling. Each theory, then, tells a different story about reality. Einstein's relativity paints a universe of geometry, smooth, deterministic, where cause and effect are woven into the curvature of spacetime. The future is fixed, the past immutable. Time is a dimension, but one that bends, stretches, slows. Reality is a block, unchanging, eternal. Gravity is its shape. Quantum field theory demands a universe of probability, where particles flicker in and out of existence, where observation collapses, waves into particles, where entanglement defies locality. Gravity, in this story, must be quantized, must have a carrier, a graviton, a wave function, but it resists. And so reality fractures, two sets of rules, two domains, two truths. Gravity remains the outsider. Emergent gravity suggests a universe of information, where space-time is not fundamental, but derived, where gravity is not cause, but consequence, where the cosmos is not governed by forces, but by statistics, by entropy, by forgetting. Reality is approximate, a coarse-grained illusion emerging from quantum noise. Causality is not broken, it is statistical. Time is not fundamental, it is counted. Gravity is not real, it is remembered. The holographic principle whispers a universe of encoding, where all that is written on the edge, where black holes are not voids, but hard drives, where space-time is not stage, but projection. Reality is two-dimensional, gravity, an artifact, existence, a computation. The collapse of time hypothesis dares to say, gravity is not force, not geometry, not information. It is memory, the residue of duration's decay, the fossil of temporal contraction. What does this mean for causality? In Einstein's universe, causality is preserved but bent. Light cones tilt near massive objects. Event horizons sever time, but within each local frame, cause precedes effect. In quantum gravity, causality phrase. Virtual particles borrow energy from the vacuum. Entanglement links distant events instantaneously. Closed time-like curves, theoretical paths looping backward in time, appear in certain solutions. Causality becomes probabilistic, not absolute. In emergent gravity, causality is thermodynamic. Effects follow causes, not because of fundamental law, but because entropy increases. Time's arrow is not imposed, it is statistical. The past has higher order, the future higher disorder. Gravity follows the gradient. In the collapse of time view, causality is archival. Every effect is the memory of a prior temporal state. Falling is not caused by mass, it is the recall of time's thickening. Orbiting is not motion through space, it is tracing the grooves of duration's collapse. Causality is not linear, it is sedimentary, layer upon layer of collapsed moments, each preserved in geometry. And what of existence itself? If gravity is emergent, then matter too may be emergent. If spacetime is holographic, then solidity is illusion. If time collapses, then presence is memory. The rock beneath a foot, the light from a star, the warmth of a hand, all may be patterns, temporary configurations in a deeper quantum field, stabilized by entropy, shaped by information, preserved by gravity's gentle pull toward equilibrium. Existence is not substance, it is structure, not permanence, but persistence. Even consciousness, that most intimate mystery, may be entangled with this. Some theorists, like Roger Penrose and Stuart Hameroff, propose that consciousness arises from quantum processes in microtubules, processes sensitive to space-time geometry. If gravity is the curvature of time, and time is emergent from quantum information, then mind too may be a phenomenon of collapsed duration, a localized knot of memory, self-referencing, self-preserving, not proven, not testable, but hauntingly plausible. If gravity is memory, and mind is memory, then perhaps both arise from the same source. The equations do not yet unify, but the patterns converge in loop quantum gravity. Space-time is granular, woven from spin networks, evolving in discrete steps. Time is not continuous, it is counted. Gravity emerges from quantum geometry. In causal set theory, space-time is a collection of events, ordered by causality. Time is the sequence, gravity the structure. In string theory, gravity is the vibration of strings in higher dimensions. But even here, the ADS-CFT duality suggests gravity is encoded holographically on lower dimensional branes. In all cases, gravity is secondary, derived, emergent, remembered, laboratories inch closer. In 2023, researchers at Fermilab's holometer, a device designed to detect quantum fluctuations of spacetime itself, placed the tightest constraints yet on Planck-scale holographic noise. No signal was found, but the search continues. If spacetime is pixelated, if gravity is emergent, the noise should be there, a whisper beneath the silence. Quantum simulators now model entanglements linked to geometry in controlled systems of ultra-cold atoms or superconducting qubits. Physicists create synthetic spacetimes and observe how entanglement entropy generates effective curvature. The ER equals EPR. Conjecture that entangled particles are connected by microscopic wormholes gains experimental plausibility. Even cosmology bends toward memory. The cosmic microwave background, the afterglow of the Big Bang, shows temperature fluctuations that match predictions of inflation. But some anomalies, large-scale asymmetries, unexpected correlations, resist explanation. Could they be imprints of pre-Big Bang quantum information, echoes of a deeper structure, gravity as memory, preserving not just the universe's birth, but hints of what came before? The graviton remains unseen, not because it is hidden, but because it may not exist, not as particle, but as pattern, not as force, but as fossil. And so the theories spiral, each more beautiful, each more unsettling. Einstein gave us geometry. Quantum theory demands particles. Verland offers entropy, T-Hooft and Susskind whisper holograms, and the collapse of time hypothesis, still unnamed, still unproven, dares to say gravity is the scar of duration, the wrinkle in memory, the echo of time's first fall. What is real, then? If gravity is not fundamental, what is? Information, entropy, time, or is even time emergent, rising from quantum correlations, from causal relations, from the growth of entanglement? Perhaps the only fundamental thing is relation. Connection, difference, and gravity, the gentle pull toward. Equilibrium is the universe's way of remembering that it was once whole. Each theory is a story. Einstein's the universe as sculpture, shaped by mass, frozen in 4 dimensions. Quantum's the universe as storm, probabilistic, flickering, uncertain. Verland's the universe as ocean, waves emerging from unseen depths, tides pulled by entropy, holographic. The universe as dream, projected from a surface, illusory yet consistent. Collapse of time, the universe as archive, every fall, every orbit, every black hole, not an event, but an entry, not motion, but memory. And perhaps all are true at different scales, in different languages, seen from different angles. Gravity is geometry on planetary scales. Gravity is entropy on galactic scales. Gravity is holographic near black holes. Gravity is memory in the quantum foam. The universe does not choose one truth, it layers them. And so the final question lingers, quiet, vast, unanswerable. If gravity is the memory of time's collapse, then what, or who, is remembering? The equations offer no answer, only silence, and the slow, patient fall of apples, of stars, of light through thickening time, still bending, still folding, still becoming memory, still becoming gravity, still becoming what was. The universe does not whisper its secrets, it sings them in frequencies too low for ears, in curvatures too subtle for eyes, in durations too fine for clocks. To hear it, humanity built instruments, not of wood or wire, but of laser beams stretching kilometers, of mirrors suspended in vacuum, of atomic hearts chilled near absolute zero, of telescopes orbiting beyond the atmosphere, peering into the first light of time. These are not tools of conquest, they are tools of listening. Gravity, that quiet architect, that memory of collapsed time, leaves traces, not in force, but in form, not in pull, but in pattern. And across laboratories, mountaintops, and the silent void of space, scientists now trace those patterns, not to confirm what is known, but to uncover what is hidden. The anomalies grow louder, the equations tremble, and the instruments, ever more sensitive, ever more precise, begin to hear the echo beneath the silence. It began with a chirp on September 14, 2015, at 9 hours, 50 minutes and 45 seconds UTC, a signal washed over Earth, not through air, not through matter, but through space-time itself. designated GW150914. It lasted 0.2 seconds. A rising tone from 35 Hz to 250 Hz, like the sigh of a cosmic string plucked in the dark. It came from 1.3 billion light-years away. Two black holes, 236 and 29 solar masses spiraling, merging, vanishing into a single, heavier whole. In that instant, 3 solar masses were converted into pure gravitational energy, ripples in space-time propagating outward at light speed, detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. The signal confirmed Einstein's final, untested prediction. Gravitational waves exist. Space-time is elastic. It rings. It remembers. But LIGO heard more than waves. It heard time. The waveform, the precise shape of the chirp encodes the dynamics of space-time curvature near the merger. General relativity predicts its form with astonishing accuracy. But deviations, even minute, could signal something deeper. Quantum corrections to gravity, emergent geometry, memory effects from prior states. So far, no deviation has been found, but the search continues. LIGO, joined by Virgo in Italy and Kagra in Japan, now listens constantly, not just for black holes, but for neutron star collisions, supernova, cosmic strings, and even primordial waves from the Big Bang. Each detection is a stress test for gravity's nature. Does space-time ring like Einstein's smooth fabric, or does it crackle at Planck scales with quantum grain? In 2023, LIGO's fourth observing run began with upgraded sensitivity, capable of detecting mergers out to 5 billion light-years. With each new chirp, physicists compare the waveform against not only general relativity, but against alternative models, Verlin's emergent gravity, scalar tensor theories, massive gravity, holographic corrections. No anomaly yet. But the silence is not absence. It is patience above the atmosphere. Other eyes watch. The James Webb Space Telescope, humanity's deepest gaze into cosmic time peers, not at gravity directly, but at its consequences. At galaxies forming just 300 million years after the Big Bang. At gravitational lenses magnifying the earliest stars. At the distribution of mass, visible and invisible, across cosmic webs. Webb's data sharpens. The dark matter mystery. Galaxies in the early universe rotate too fast. Clusters bend light too strongly. Structures formed too quickly. All point to unseen mass or to misunderstood gravity. In 2023, Webb observed galaxy CEERS 2112, a barred spiral. Mature and structured, existing when the universe was only 2 billion years old. According to simulations based on dark matter, such galaxies should not yet exist. They require time and mass to form. Yet here it is, ordered, symmetrical, rotating, emergent gravity models, which require no dark matter, predict such early structure more naturally. In Verlin's framework, visible baryonic matter alone, through its entropic displacement of quantum information, generates sufficient curvature to explain rotation and lensing. No halos required. Webb does not confirm this, but it does not rule it out. Each image, each spectrum, each redshift is a question carved in light. Is dark matter real, or is gravity remembering something else? Euclid, the European Space Agency's cosmic cartographer, launched in 2023, now maps the geometry of the universe in 3 dimensions. Over 6 years, it will image 2 billion galaxies, measuring their shapes, positions, and redshift. Its goal: to trace the invisible hand of dark matter through gravitational lensing, and to measure the acceleration of cosmic expansion driven by dark energy. But Euclid also tests gravity itself by comparing the distribution of galaxies with the distortion of their light. Weak lensing, it can reconstruct the gravitational potential across cosmic history. If gravity behaves differently on large scales, if it is emergent or time-collapsed, the maps will show it. Preliminary data, released in late 2024, already reveals anomalies, unexpected voids, overdensities that don't align with CDM predictions, the standard model of cosmology. Not yet statistically significant, not yet revolutionary, but the patterns are there, like brushstrokes beneath a painted surface, hinting at an older image. Gravity on cosmic scales may not be what we thought, and soon the silence of space will be pierced by a new ear. LISA, the Laser Interferometer space antenna, scheduled for launch in the mid-2030s, will consist of 3 spacecraft flying in a triangle 2.5 million kilometers wide, linked by laser beams, floating free of Earth's seismic noise. LISA will detect low-frequency gravitational waves from supermassive black hole mergers, from binary systems in our galaxy, from cosmic phase transitions in the early universe. LISA will hear what LIGO cannot: the slow, deep groans of space-time, waves with wavelengths longer than Earth's orbit. In these frequencies, subtle deviations from general relativity may appear, echoes from quantum horizons, memory imprints from prior cosmic cycles, signatures of emergent geometry. LISA may even detect the gravitational wave background, the hum of countless unresolved mergers, the whisper of the universe's violent youth. If gravity is the memory of time's collapse, that hum may carry the echo of the first temporal contractions, the moment duration began to thicken. Beneath the Earth's surface, in tunnels colder than deep space, other experiments probe gravities. Future colliders, like the FCC, do not search for gravitons directly. The energy required to produce one is 10 times higher than current machines can reach, but they search indirectly for extra dimensions, for quantum gravity effects in high-energy collisions, for particles that could mediate gravity in hidden sectors. In 2012, the Higgs boson was found, completing the standard model, but no sign of supersymmetry, no hint of extra dimensions, no whisper of quantum gravity. Yet anomalies linger. In 2021, the Moyne G2 experiment at Fermilab measured the magnetic moment of the Moyne and found it slightly stronger than predicted. A crack in the standard model, a hint of new physics, perhaps a shadow of gravity's deeper structure, leaking into quantum fields, not confirmed, but not dismissed. And then the clocks, not the clocks of towers or wrists, but atomic hearts, tuned to the vibration of cesium, of strontium, of clocks so precise they lose less than 1 second over the age of the universe. These clocks do not merely keep time, they measure gravity's memory. In 2022, researchers at Gila in Colorado compared two optical lattice clocks, one raised just 1 millimeter above the other. The lower clock, deeper in Earth's gravity well, ticked slower by 1 part in 10. a difference of 0.000000000000000000001, yet measurable, confirmed. Time bends, not metaphor, not theory. Measurement, and in that measurement, a clue. If gravity is the collapse of time, then even a millimeter of elevation should reveal not just dilation, but structure, entropy gradients, information displacement, memory density. Future clocks, optical, nuclear, based on thorium transitions, aim for 100 times greater precision. At that level, they may detect not just gravitational time dilation, but quantum fluctuations in space-time itself. The foam predicted by quantum gravity, the pixelation of duration. If time is emergent, these clocks will see its grain. Black holes, once theoretical, now stare back. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole, M87*, 55 million light-years away. A dark shadow, ringed by fire, the silhouette of the event horizon, bent by gravity's hand. In 2022, Sagittarius A*, the black hole at the Milky Way's heart, followed. The images match general relativity's predictions almost perfectly, but almost is where mystery hides. The photon ring, the thin band of light orbiting the black hole, should contain subring, echoes of light that circled multiple times before escaping. These encode information about space-time's geometry near the horizon. Future observations with expanded telescope arrays will resolve them. Deviations could reveal quantum structure, holographic encoding. FIREWALLS.OR. If gravity is memory, the imprint of infalling matter, preserved in the horizon's entropy, the black hole does not merely curve light, it archives it. Galactic rotation remains. The quiet rebellion, Rubin's curves, flat, unyielding, still defy Newton without dark matter. But modified gravity theories, Mond, Teves, Verlin's emergent gravity, continue to evolve. In 2024, a team using data from the Gaia spacecraft analyzed the motions of over 200,000 stars in the Milky Way's outer disk. Their velocities, precise to within 0.1 kilometers per second, show subtle deviations from both dark matter models and simple Mond, but they align tentatively with entropic gravity's predictions, not proof, but pattern, cosmic. Lensing the bending of light by mass now maps the invisible. The Hubble Space Telescope, the Vera C. Rubin Observatory, opening 2025, and Euclid trace distortions in galaxy shapes, weak lensing to reconstruct mass distributions across billions of light-years, where dark matter models predict smooth halos. Observations sometimes show clumpiness, voids, filaments that don't align. In 2023, the KID survey, the kilodegree survey, found that the observed lensing signal is 10% weaker than CDM predicts. A sigmate tension, not enough to discard dark matter, but enough to question it. Emergent gravity offers an alternative, no dark matter, but a modified response of spacetime to visible mass. The lensing is not weaker, it is differently sourced. Not from halos, but from entropy gradients. The data does not yet choose, but it is listening. And in laboratories, the final frontier, quantum experiments now probe gravity's role in decoherence, the collapse of quantum, superposition, positons. In 2021, a team at the University of Southampton placed a microscopic glass bead in superposition, levitated by laser, cooled near absolute zero. They measured how Earth's gravity caused the bead's wave function to decohere, not randomly, but directionally, toward slower time. Gravity did not merely bend space, it selected timelines. In 2024, researchers in Vienna entangled two atomic clocks, then placed them at different heights. The entanglement degraded faster for the lower clock, not because of noise, but because of time dilation. Gravity enforces classicality. It erases quantum possibilities, not by force, but by memory. If gravity is the collapse of time, then it is also the collapse of quantum uncertainty. The universe remembers, and in remembering, chooses. The anomalies accumulate, not as failures, but as whispers. The muon's magnetic moment, the galaxy too early. The lensing, too weak, the clock to slow. The black hole, too silent, the wave too smooth. Each is a thread tugging at the fabric of understanding. What are they revealing? That gravity is not broken, but layered. Space-time is not fundamental, but emergent. That time is not flowing, but collapsing. That mass is not source, but marker. That the universe is not expanding, but remembering. The tools grow sharper, richer, the silence thinner, and beneath it, a hum, the echo of duration's first fall, still ringing, still folding, still becoming gravity, still becoming memory, still becoming what the instruments are only now learning to hear. It begins and ends with a fall, not with violence, not with rupture, but with surrender. An apple detaches, a star collapses, a photon arcs around a galaxy, a human body, weary, lies down to rest, all drawn, not by force, not by command, but by the quiet slope of time itself, thickening beneath them, slowing, settling, remembering. What if every descent, every orbit, every spiral, every silent plunge into darkness is not motion through space, but motion into memory? What if gravity is not the architect of the future, but the archivist of the past? The equations do not lie. Time slows near mass, measured, confirmed. Atomic clocks, satellites, pulsars, all whisper the same truth. Duration is not universal. It is local, personal, shaped by presence, by weight, by collapse. Mass does not merely bend space, it thickens time, and objects do not fall because they are pulled. They fall because time flows slower below, and motion, left to itself, follows the gradient of duration toward stillness, toward equilibrium, toward entropy's quiet victory. In this light, gravity is not a force, it is a fossil, the residue of temporal contraction, the echo of moments that have already passed, sedimented into geometry, preserved in curvature, replayed as motion. Every orbit is not a path through space. It is a groove in time's record, worn by repetition, deepened by memory, traced again and again by bodies that do not choose, but recall. Consider the moon. It does not circle Earth because it is lured by invisible strings. It glides, weightless, eternal, along the contour of collapsed duration. The Earth's mass has slowed time in its vicinity. The moon drifts toward that slowing, not out of attraction, but out of tendency. Like water finding its level. Like heat diffusing, like memory returning to where it was formed, the tides rise not because the moon pulls, but because Earth's oceans remember the shape of time's fold and conform to it. Even light, massless, swift, defiant, bends near stars, not because it obeys gravity's command, but because it traces the slope of time's collapse. A photon has no choice. It follows the straightest path, and in curved time, the straightest path is bent gravity. Then is not law, it is liturgy, a ritual of remembrance, performed by planets, by stars, by galaxies, by falling leaves, by beating hearts, by breath. Humanity's search across centuries, across continents, across equations, has never been only for gravity. It has been for time, for the nature of duration, for the reason why moments do not return, why causes precede effects. Why entropy rises. Why memory fades, and yet gravity endures. Newton sought law and found universality. Einstein sought geometry and found relativity. Quantum theorists sought particles and found silence. Verlaine sought entropy and found emergence. Each, in their own way, was tracing the same shadow, the shadow of time's collapse, not its flow, its fall. And so the cosmos reveals itself, not as machine, not as accident, not as explosion, but as archive, a vast, silent library where every event is recorded, not in ink, but in geometry, where black holes are not voids, but vaults, where galaxies are not structures, but inscriptions, where the expansion of space is not growth, but forgetting. Dark energy, that mysterious acceleration, may not be a force pushing outward. It may be time thinning, the universe diffusing its memory, stretching its record, cooling its past into emptiness. Dark matter, that invisible scaffolding, may not be substance at all. It may be the contour of time's collapse around visible stars. Spacetime, elastic response to entropies, gradient mimicking mass where none exists. The universe does not need ghosts to hold itself together. It needs only memory. And what of consciousness? That flicker of awareness, nested in bone, humming in synapse, trembling in thought. Is it too entangled with this? If gravity is the memory of time's collapse, and mind is the memory of experience's collapse, then perhaps both arise from the same source, not substance, but structure, not permanence, but pattern. Roger Penrose once speculated that consciousness emerges from quantum processes in microtubules, processes sensitive to spacetime geometry. If spacetime is emergent, if time is collapsed information, then mind, too, may be a localized knot of memory, self-referencing, self-preserving, self-aware, not proven, but haunting. If gravity remembers, and mind remembers, then perhaps both are echoes of a deeper unity, a cosmos that does not merely exist, but recalls itself into being. The instruments grow sharper, the data richer. LIGO. Here's spacetime ring. Web sees galaxies too soon. Euclid maps invisible contours. Atomic clocks measure time's grain, and still no final answer. Only deeper questions. Is the universe expanding, or is it remembering less? Are black holes destroying information, or preserving it encoded, scrambled, holographed on their horizons? Is time flowing forward, or collapsing inward, layer by layer, moment by moment, into the geometry we call gravity? Perhaps existence itself is the residue, not of matter, not of energy, but of time's own surrender. The Big Bang was not a beginning. It was the first fold. The moment duration began to thicken, differentiate, to accumulate, and gravity, the echo of that fold, still propagating, still shaping, still remembering. Every star that forms, every planet that cools, every life that stirs, every thought that rises, all are not building the future. They are replaying the past, not as repetition, but as resonance. And so, the final reflection: what does it mean to live inside gravity? Not as force, not as field, but as memory. To walk on Earth is not to be pulled downward. It is to rest within time's deepest pool, where duration has settled, thickened, slowed, and holds you gently in its residue. To gaze at the stars is not to look across space. It is to look across time, not as distance, but as archive. Each twinkle, a memory preserved in light, bent, delayed, redshifted by the folds of collapsed duration. To love, to lose, to hope, to grieve, all are not anomalies in a mechanical cosmos. They are harmonics, trembling in the same fabric that bends starlight and slows clocks. If gravity is memory, then perhaps emotion is its echo in flesh. Perhaps longing is the human name for temporal gradient. Perhaps grief is the weight of collapsed moments, too dense to escape. Perhaps joy is the rare, fleeting drift upward against entropy's slope. The equations offer no solace, no meaning, only structure. But the structure, if gravity is memory, is itself meaning. The universe does not forget it, archives, it does not discard it, curves, it does not erase. It preserves in geometry, in motion, in light. Every fall is a line in its ledger, every orbit a verse, every black hole a sealed chapter, every supernova a footnote glowing in the dark. And humanity, not outside the archive, but within it, not observers of gravity, but participants in its memory. The hands that built LIGO, that launched Webb, that chilled atomic clocks to near stillness, are not separate from the cosmos they measure. They are its recall, its self-interrogation, its quiet, trembling attempt to remember why it remembers. The closing tension is not in the data. It is in the silence between the data points, in the pause before the next gravitational wave chirp, in the gap between clock ticks at different heights, in the shadow within the black hole's silhouette, in the flatness of the galaxy's rotation curve, in the acceleration of cosmic expansion. In all these, a whisper, not of force, but of remembrance. Gravity may not be the pull of matter. It may be the ghost of time's own collapse, and we, all of us, live inside its remembrance, not as prisoners, not as accidents, but as echoes, falling, orbiting, collapsing, remembering, The apple still falls, not because the earth calls, but because time has grown heavy beneath it. The stars still wheel, not because they are bound, but because they trace the grooves of duration's collapse. The black holes still wait, not because they hunger, but because they preserve, and the universe, vast, dark, glittering, does not unfold, it refolds, layer by layer, moment by moment, memory by memory. Perhaps this is the final revelation, not that gravity is weak, not that it resists quantization, not that it emerges from entropy, but that it is, and always has been, time's elegy, the slow, patient song of duration turning into geometry, of motion turning into memory, of presence turning into past. And if that is so, then every breath drawn, every hand held, every tear shed, every star wished upon is not lost, it is recorded, not in heaven, not in myth, but in the curvature of space-time itself, in the slope of time's collapse, in the quiet, invisible force that binds galaxies and hearts together. Gravity is not the pull toward the future, it is the weight of the past still falling, still folding, still echoing, still remembering. And we, fragile, fleeting, luminous, are not outside the echo, we are inside it, living, loving, listening to the universe, remembering itself through us, through time, through gravity. The instruments will keep measuring the equations, evolving the theories, colliding, but the mystery, the true mystery, was never in the numbers, it was in the fall, in the surrender, in the quiet, in the memory. And so it ends as it began, with a fall, not of apple, not of star, but of understanding, that gravity is not what pulls us down, it is what holds the past together, and in holding it, it holds us still, always, remembering,